Hello, class. Today we're going to start covering chapter 5, which are exponential and logarithmic functions. We're going to look at covering the graphing and applying exponential functions, comparing transformations of graphs of exponential functions. We're going to graph and evaluate logarithmic functions. We're going to convert equations to logarithmic and exponential forms, evaluate and apply common logarithms, and also evaluate and apply natural logarithms. So let's start with the definition of the exponential function. If b is a positive real number, or b is not equal to 1, then the function f of x equals b raised to the x is an exponential function. Constant b is called the base of the function, and the variable x is the exponent. Now, if we look at the graph of the exponential functions, it has the general form of the equation y equals b raised to the x. You can see the graph over here on the right-hand side. It looks like we have two different options, okay? So on both of those options, you can tell that you have no x-intercept. You actually have a horizontal asymptote on the x-axis. Your y-intercept for both is 0, 1. Your domain is all real numbers, and your range is all real numbers where y is greater than 0, okay? Because it doesn't live or exist below this x-axis here. The shape is an increasing function, so matching this curve, an increasing function if b, your base, is greater than 1 and y equals b to the x. It's a decreasing function if y equals b to the x with 0 less than b less than 1. So if your base is between 0 and 1, you could have a decreasing function, or if your exponent is negative, you could have a decreasing function. Now, let's look at the transformations of graphs. So we want to explain how the graph of each of the following functions compares to the graph of y equals 3 to the x. And we want to graph each function on the same axis as y equals 3 to the x. Now we have the graph here, y equals 3 to the x, graphed here with the black line. Now, you can tell once we graph y equals 3 raised to the x minus 4 that this graph, the blue line, is shifted from the black line. Now that minus 4 is technically on the inside here. If we remember our rules, if we have a number subtracted on the inside, we're going to move that equation to the right. Okay, so here we're moving to the right 4 units. Okay, the graph stays the same shape, but is shifted 4 units right. Now, if we look at y equals 2 plus 3 raised to the x minus 4, we have our initial graph here in black, y equals 3x, or 3 raised to the x, and then our shifted graph here in the blue line is y equals 2 plus 3 raised to the x minus 4. Now, we have to determine how we shifted from the black line to the blue line. So we can tell by the previous part A, that this x minus 4 causes us to shift 4 units to the right. Now that addition of 2 on the outside is going to cause that shift of 2 units upwards. So overall, the graph has the same shape, but is shifted 4 units right and 2 units up. Also, that shifts that horizontal asymptote to y equals 2. Let's look at exponential growth models. So, y equals a times b raised to the kx. All right, you can notice the change here. We're multiplying by a number on the outside and potentially on the inside. So a is multiplied by on the outside, k is multiplied by on the inside. B is still greater than 1, a is greater than 0, and k is greater than 0. We don't have an x-intercept, but we have adjusted our y-intercept to be 0 to a. Okay, that 1 adjusted to an a on the outside. The domain here is the set of all real numbers. The range is all real numbers where y is greater than 0. The horizontal asymptote is the x-axis, where the line y equals 0. We have a shape of increasing on the domain and concave up. Let's try an example. The total personal income in the United States in billions of dollars for the selected years from 1960 and projected to 2018 to be modeled by y equals 492.4 times 1.07 raised to the x, with x equal to the number of years after 1960. We want to know, what does the model predict the total U.S. personal income to be in 2014? And we also want to graphically determine the year during which the model predicts the total U.S. personal income will reach 28.5 trillion. Now, starting with part A. In order to determine what the model predicts the total U.S. personal income to be in 2014, we have to take into account that 2014 is 54 years after 1960. So we have to make that year adjustment here because we're doing years after 1960. Okay, so that means we need to plug in an x value of 54. So we're going to plug in an x value of 54 into our initial equation. So if we plug a 54 in for our x right here, we will be able to solve on our calculator 492.4 times 1.07 raised to the 54. Let's try that. So we're going to do what I say, 492.4 times 1.07 raised to the 54. And that's where we get 19,012.62311. All we're doing from there is approximating to the nearest billion. So we wind up with 19,013 billion. Or if we wanted it in trillions, it would be 19.013 trillion. Now, we also want to graphically determine the year during which the model predicts that the total U.S. personal income will reach 28.5 trillion. Now, in order to do this, we're going to graph the initial model on Y1. I'm going to graph Y equals 28,500 on Y2. The reason we're graphing 28,500 instead of 28.5 is because the 28.5 is in trillions. And if you remember, we initially had our equation here in billions of dollars. We need to make that conversion and stay in billions when we do our calculations. So let's come over here on our calculator. We are going to put our initial graph in our Y1, clear out anything in your Y1s and Y2s. And our initial graph here was 492 something. Let's see. Make sure I get it right. 492.4 times 1.07 to the x. Okay. And then in Y2, like I said, we're going to put in our 28,500. And then you can zoom a standard zoom, but you probably won't be able to see it. I'm going to do a zoom fit. On the zoom fit, you can see the two curves, but you can't see where they intersect. And where they intersect is what we're concerned with. So from here, I'm just going to zoom out. Hit enter, hit enter. At two zoom outs, and I'm able to see where they intersect so that I can go second calc, intersect, first curve, second curve, hit enter twice, and then scroll over to where you think they intersect and hit enter a third time. We wind up with an x value of 59.98, so approximately 60. 60 years after 1960 is when we should reach this value. So, like I said, you can see on this graph as well, copied over here, it says the intersection feature gives about y equals 59.98, or about 60. Therefore, the model predicts that in 2020, the U.S. personal income will reach 28.5 trillion. Keep in mind they come up with the 2020 because they're doing 1960 plus the 60 that you just found. That's what gives you 2020. Now, let's also look at some exponential decay models. Now, an exponential decay model, as you can see here, instead of increasing, it goes down and decreases. So we have y equals a times b raised to the kx, where b is greater than 1, a is greater than 0, and k is less than 0. Or we can have y equals a times b raised to the kx, where 0 is less than b is less than 1, a is greater than 0, and k is greater than 0, essentially making the base a number between 0 and 1, or making the exponent negative. Okay, our x-intercept is none, our y-intercept is 0, a, Domain is all real numbers. Y is greater than 0. Horizontal asymptote is your x-axis, and the shape is decreasing on the domain and concave up. Now let's look at an example for sales decay. It pays to advertise, and it is frequently true that weekly sales will drop rapidly for many products after an advertising campaign ends. This decline in sales is called sales decay. Suppose that the decay in sales of a product is given by S equals 1,000 times 2 raised to the negative 0.5 x dollars, where x is the number of weeks after the end of a sales campaign. Use this function to answer the following. What is the level of sales when the advertising campaign ends? What is the level of sales 1 week after the end of the campaign? Use the graph of the function to estimate the week in which sales equals to 500. According to the model here, will the sales ever fall to 0? Now, start with part A. What is the level of sales when the advertising campaign ends? Well, when advertising campaign ends, that's week 0. So we need to set x equal to 0. If we set x equal to 0 in our equation here, here's where the x would be. We have 1,000 times 2 raised to the negative 0.5 times 0. Now, anything times 0 is 0. Anything raised to the 0 is 1. So basically get 1,000 times 1, and we can see that at the end of our advertising campaign, we should be making $1,000 at week 0. Well, how about week 1? The end of week 1, x equals 1. So we need to plug 1 in for x in our equation. So I have 1,000 times 2 raised to the negative 0.5 times 1. If you use your calculator to simplify that, you should come up with about 707.11. So $707.11 at the end of week 1. Now, let's use our graph function to estimate the week in which sales will equal $500. Okay, so in order to do that, I need to type in the initial equation. Okay, so I need to type in the initial equation, which is 1,000 times 2 raised to the negative 0.5x. I clear out everything that I have in my y1s. I do 1,000 times 2 raised to the negative 0.5x. And then in my y2, I need to type 500. I can graph that on the zoom I have, and they should be able to see some kind of intersection point there. You can try to zoom standard on it, but zooming standard is probably not going to show you very much. You can then zoom fit from there as well if you want to. That gives you a little bit better zoom to see where they intersect at. I'm going to do second calc, find that intersection point. So first curve, second curve, then I'm going to scroll down here to guess. And I wind up with 2 and 500. So x equals 2 when y is 500. Okay, so we can see that y equals 500 when x equals 2. Thus, sales fall to half of their original amount after 2 weeks. So our answer here is essentially is 2, or 2 weeks. Now, according to the model, will the sales ever fall to 0? Let's look at the model again. So if we look at the model, let's say we zoom out a bit. We zoom out a bit. Does the blue line ever really cross the x-axis? Now we should know from the definition that we have a horizontal asymptote at our x-axis, which means it approaches but never reaches. So the graph of the sales decay function approaches the positive x-axis as x gets large, but it never reaches the x-axis. The sales will therefore never reach a value of 0. It'll just get really, really close to it. Now, let's look at the number e. Because we're messing with logarithms, natural logarithms, exponentials, we need to know what the number e is. The number e is an irrational number with a decimal approximation of 2.718281828. And it can be located on your calculator. If you want to use the direct e button here, kind of take us to a blank screen. If you want to use the direct e button here, it's located on top of the divide. So you just have to do second divide and it gives you the e, and you can see the decimal approximation. If you want to do the e raised to an exponent button, you can do that as well. E raised to the first is obviously the same thing as e, which is 2.718281828. Okay, and you can also, using the exponent button, plug in other values as well to get other expanded exponentials there. All right, let's try an example. It says carbon-14 dating. During the life of an organism, the ratio of carbon-14 atoms to carbon-12 atoms remains about the same. When the organism dies, the number of carbon-14 atoms within its carcass begins to gradually decrease. The number of carbon-12 atoms does not. So they can be measured to determine how many carbon-14 atoms were present at death. The number of carbon-14 atoms in an organism when it is discovered can then be compared to the number present at death to find out how long ago the organism lived. The ratio of the present amount, y, of the carbon-14 to the original amount, y naught, t years ago is given by y over y naught equals e raised to the 0.000120970. Now, that produces the function y equals f of t, which equals y naught times e raised to the 0.000120970t. It gives the amount remaining after t years. If the original amount of carbon-14 present in an artifact is 100 grams, how much remains after 2,000 years? Okay. Well, the original amount is represented by y naught. That is 100. Okay. T represents time. Time here is 2,000 years. So we should be able to know what we're substituting into our equation. So the initial amount, y naught, is 100 grams. The time, t, 2,000 years. So we substitute these into our equation. So we have f of 2,000 equals 100 times e raised to the negative 0.000120970 times 2,000, which gives us about 78.51. Let's make sure we can type that in our calculator. So I'm going to pull my calculator up. I'm going to type in 100 times e raised to the negative 0.0001297, and then we're going to plug in 2,000 for the year. If we do that, we get that 78.51. So about 78.5 grams are present after about 2,000 years. Let's now look at the definition of a logarithmic function. So for x greater than 0, b greater than 0, and b not equal to 1, the logarithmic function with base b is y equals log base b of x, which is defined by x equals b raised to the y. That is, log base b of x is the exponent to which we must raise the base b to get the number x. The function is essentially the inverse function of the exponential function y equals b to the x. So let's try some of these examples. We want to write each of the following exponent equations in logarithmic form. So essentially, you'll be given these and expected to produce these solutions. Now, we're converting from exponential form to logarithmic form. Okay, in order to do that, this is your base of your logarithm. This is what goes on the inside of the logarithm, and this is what goes on the other side of the equal sign. So you can see the conversion of the first one, 3 squared equals 9, is converted into log base 3 of 9 equals 2. 4 raised to the negative 1 power equals 1/4 is converted into log base 4 of 1/4 equals negative 1. 5 raised to the first power equals 5 is converted into logarithmic form as log base 5 of 5 equals 1. X equals 3 raised to the y is converted to log base 3 of x equals y. Okay, log base 3 of x equals y. So we have to be able to do these conversions. And if you can notice, most or all of these here are true statements. 3 squared is 9, 4 raised to the negative 1 is 1/4, and 5 raised to the first power is 5. And then converted into the logarithmic form, all those true statements hold as well. Like I said, we have to be able to convert from one side to the other. So we also might be given a logarithm and expected to convert to an exponential. Okay. So if we're given log base 2 of 16 equals 4, we should be able to convert that into 2 to the 4th power equals 16. If we're given log base 10 of 0.001 equals negative 4, we should be able to convert that into 10 to the negative 4th power equals 0.0001. And for C, log base 6 of 1 equals 0 should be easily converted into 6 to the 0 power equals 1. Now, let's try to graph this one. It says a graph log base 5 of x. I'll put that on my calculator here. Okay, if I go to y equals, I'm going to clear out anything I had in here. I want to be able to graph this logarithmic function. The best way to do this is to hit the math button once you're into y1, is scroll down and use the log base application here. This is going to bring it up to where you can put the 5 in the base here and click over and put the x inside of the parentheses. Then I can do a zoom standard, and I have graphed the log base 5 of the x function here. That is the simplest way to do it. Now let's look at the PowerPoint. Okay, you could graph this by hand by plugging in different values of x, coming up with different values of y, and get the same graph, but we have the computing technology just to be able to graph it on our graphing calculator. Overall, let's look at some properties of the logarithmic function. So we have the equation y equals log base b of x, an x-intercept of 1, 0. So here we have an x-intercept of 1, 0 instead of a y-intercept of 1, 0. Like I said, it's kind of the opposite of the exponential function here, the inverse of it. Our y-intercept here is none. Our domain is x is greater than 0. Our range is all real numbers. And here we have a vertical asymptote on the y-axis. So you can tell it gets really close to this y-axis, but it never crosses it. And we could have an increasing function, or we could have a decreasing function. All right, let's look at some shifts. Here we want to explain how the graph of each of the following functions compares to the graph of y equals log of x. We want to find the domain and graph each function. Okay, so it says y equals the log of x plus 3. Now, if you see the graph here, here's y equals the log of x. Here's the graph of y equals the log of x plus 3. Keep in mind that 3 is on the inside, and it's positive. So we should have a shift to the left, 3 units. So it says the graph of y equals the log of x plus 3 has the same shape as the graph of y equals the log of x, but is shifted 3 units to the left. Like I said, 3 units to the left. Okay, because the graph has been shifted 3 units to the left, now the domain has been shifted from 0 to infinity to basically -3 to infinity. Let's look at y equals 4 plus the log of x minus 2. Now here, the 4 is on the outside, that moves it up and down. The 2 is on the inside, that moves it either left or right. We can already see the graph compared over here on the right-hand side, and we can tell that there's been a shift to the right and a shift up. So we have shifted here 2 units to the right and 4 units up. So the graph of y equals 4 plus the log of x minus 2 has the same shape as the graph of y equals the log of x, but it is shifted 2 units to the right and 4 units up. The vertical asymptote is therefore shifted right as well, and is x equals 2. Now we have a domain of 2 to infinity. Something you might also see is natural log functions. Now the logarithmic function with base e is y equals log base e of x, defined by x equals e raised to the y for all positive numbers x, and denoted by the natural log of x equals the log base e of x. Now keep in mind that ln is indeed an L, a lowercase l, and an n. Okay, it's not a 1 and an n, it's not a vertical line and an n, it's not I think trying to think of anything else that people, it's not a capital I and an N, it's an L. This is an L. An L, and an N. Sometimes I write it in cursive so that you can tell it's an L, not an I. Okay, it's an L and an N. Okay, lowercase l and an N. Make sure you input that way on my math lab so that you can get all your associated questions correct. So let's try an example here. It says projections from 2010 to 2050 indicate that the percent of U.S. adults with diabetes, diagnosed and undiagnosed, be modeled by P of x equals negative 12.975 plus 11.851 times the natural log of x, where x is the number of years after 2000. We want to graph the function, and we want to tell is the function increasing or decreasing, and what it means in the context of the application. What does the model predict the percent of U.S. adults with diabetes will be in 2022? And we want to use the graph to estimate the year in which this model predicts the percent will reach 33%. So let's graph the function to start with. See, I already have a graph here. Let's see and make sure we can put it in on our TI calculator. So we're looking at y equals negative 12.975 plus 11.851 times the natural log. That natural log button is found right next to the 4 button of x. Okay. Now, we graph that one. We can see here, got on standard zoom, we can see it kind of goes up. You can zoom fit it if you'd like and get a little bit better view maybe, or you can zoom standard and then you can zoom out if you want a little bit more of an outward view of how it looks. Okay, we've got a view of it here. We've graphed it, checked off part A. Okay, now based on the graph that we have, which is the same on the picture as it is here, is the function increasing or decreasing? And what does it mean in the context of the application? We can clearly tell it's increasing. It starts increasing kind of rapidly, but it slows a little bit on this increase. But the function is increasing, which means that the percent of US adults with diabetes is predicted to increase from 2010 to 2050. Okay, so what does this model predict the percent of US adults with diabetes will be in 2022? Now, keep in mind that this is the number of years after 2000. How many years after 2000 is 2022? 22 years after 2000. So what we actually need to do is we need to plug 22 into our equation. Okay, so you can plug 22 into your equation here. You can solve it out on your calculator. And you can see that you'll have 23.7. Okay, the other thing you can do, since you already have it graphed on your calculator, is you can go second graph or second table, and you can scroll down to the x value of 22 and also get the answer this way, 23.657. If you're looking at the graph itself, you could also do second calc value, x equals 22, and hit enter. And as long as you can see where x is 22, you can find it, 23.656944. Here, we're just rounding to one decimal place of 23.7. Now let's use the graph to estimate the year in which the model predicts the percent will reach 33%. So back to the graph. We want the model to reach 33%. So we want y2 to be 33. If I graph that, I need to be able to see where they intersect. Here I can't quite see where they intersect on my graph. So what I need to do is zoom out until I can see where they intersect. I zoomed out one more time. Now I can see where they intersect. When I can see where they can intersect, I can do second calc, run the intersect function, hit enter on the first curve, enter on the slope. I have to get it where it actually shows up on the first curve. So enter on the first curve, enter on the second curve, and then I'll use the cursor to get near where they intersect, hit enter a third time. And it gives me a value of 48.396111. Okay, so approximately 4849. All right, so the percent is 33% when x is approximately 48.4. If I round that up to the nearest year, that will be during the year 2049. Keep in mind it's 2049 because this year's after 2000. And if I, like I said, if I round this up, to the nearest year, to 49, and add that to 2000, that's where the 2049 goes, or comes from. That completes this first section of chapter 5. If you have any questions, feel free to email me and reach out. Other than that, give your My Math Lab homework a try, and I will see y'all